Here we're going to look at what's called a numerical derivative, or the symmetric difference quotient would be what we call it in this case. And this is just your calculator's technique for finding derivatives. So just to refer to this picture here, the definition of the derivative we came up with, or we introduced in prior videos, had a as kind of an anchor point, and then we computed the derivative by taking the limits of the slopes of the secant lines as we come from one side. But here, just to give you an alternative, there's other ways you can think about secant lines that whose slopes converge to the slope of the tangent line. And here's another picture. So let's say I wanted the slope of the curve at x equals a. So I'm looking for the slope of the tangent line at the point a comma f of a. Well, rather than approach from one side, rather than consider the point a f of a, I could just go out a distance h on the x-axis on the right and the left-hand side, and consider the slope of the secant line that's created by using those points. So I've got my two new x values, a plus h and a minus h. So this output would be f of a minus h. This output would be f of a plus h. And now you can see that the change in y, when computing my slope, would just be f of a plus h minus f of a minus h. And then my change in x would be 2h, right? H minus negative h would be 2h. So, all in all, the slope of that secant line would be f of a plus h minus f of a minus h divided by 2h, and that's called the symmetric difference quotient. And you can compute the derivative numerically. You can compute the derivative numerically by just taking your h to be really small. So if you just let h be 0.0001 or something, you're going to get a really good approximation of the slope of the tangent line. And the smaller you make h, the better the approximation will be. And so this is probably what your calculator does, because it doesn't know calculus, it doesn't know any theory, but it can compute. So it can compute these secant lines. Visually, you should see that these, as h gets smaller and smaller, you're just going to get secant lines that straddle this point, and more the slopes are going to approach the tangent line. On the next slide, we're going to talk about why this can create problems at certain instances, and why you don't want to always trust your calculator. Alright, here I just want to look at two functions that look almost identical from a distance, but whose behavior is very different at x equals 0. So I've got absolute value of x plus 1, and then I've got the square root of x squared plus 0.001 plus 1. Now in this graph, they look exactly the same, at least from this distance. So if I just unhighlight them, you can see they look exactly the same. However, one of them is differentiable at x equals 0, and the other is not. And the difference is that if we start zooming in on this corner, or what looks like a corner, the differentiable function is going to start behaving like a line, or looking more and more like a line, whereas the one that's not differentiable will never do that. So a big idea in calculus is that differentiability essentially means locally linear. And later in the course, or later in your calculus experience, you'll learn that we use lines when possible to approximate functions, because around the point of tangency, if they're tangent lines, they do a very good job of approximating the function, so the error can be contained. So let's just see this firsthand. I'm going to zoom in on the quote corner of this function and watch what happens. So you can see it rounding, and if we zoom in far enough, sure enough, it basically looks like a line. Right? At this scale, you wouldn't be able to distinguish it from a line. It looks like a line. So it's locally linear. That's why it's differentiable at x equals 0. Compare that to absolute value of x plus 1. If we keep zooming in, no matter what we do, no matter how far we zoom in, that corner will always be a corner. So that is not differentiable at x equals 0. Now this is important because if you punch these both into your calculator, if you have a TI 83 or 84, and you find the derivative at x equals 0, it's going to give the value 0 for both of these. In other words, it's going to think that absolute value of x plus 1 is differentiable at x equals 0, which it's not. So in the next slide you'll see what it does and why it does that, but you'll need to know to ignore that answer, or just never to use your calculator at those moments where we know it's not differentiable, or you aren't sure. You would need to use some theory instead. So let's just see what your calculator does. If you try to take the derivative of absolute value of x plus 1, you'd type this in. You'd go to the quit screen and type in nderiv. Now you can find that for those who've never done that before. When you go to the quit screen, go to math, and then go down all the way to number, on my calculator it's number 8, nderiv. And then you can either put the function in, or you can put it into y1, which is what I did, and then go to refer to it by hitting vars, and then go to function, yvars function y1. So I'm just going to say put this in y1. Nderiv y1, the derivative with respect to x, so I'm going to put an x in, comma, and then 0. And now we know the answer to this should be undefined, but the calculator returns 0. Alright, so that's one reason why you don't want to trust your calculator all the time, because what it's essentially doing is it's calculating the slopes of those secant lines that surround the point of interest. But it just thinks, because it's going over a distance h on both sides, it's thinking that the limit of the slopes is 0, which we know it's not. Okay, you can do the same thing. I put this second function into y2, and when you calculate the derivative, it will also return 0, this time correctly. But again, so that's the second one's correct, the first one is incorrect. So just the way that the calculator is computing it is not always going to return the right answer. So you'll want to be aware of that. This is one of those instances where calculators and computers, as great as they are, they still don't have theory to sort out some of these issues. So that's where you come in. So just be aware of that, and know when the calculator is going to give you a correct derivative and when you have to use your own understanding.